Let's talk a little bit about unit vectors. We've seen two special unit vectors so far, I and j, but there are many unit vectors, and a unit vector is any vector whose magnitude is 1. So let's say you have a vector and you want to find the associated unit vector for it. All you do is you take that original vector and divide it by its magnitude, and that will give you the unit vector that's the same direction as the original vector. This can be helpful for applications sometimes, so that's why it's worth talking about. So let's look at a couple of examples, and then we'll look at an application as well. So let's find the unit vector in the same direction as this vector, v equals 5i minus 12j. Then verify that vector actually has magnitude 1. So the first thing I need to do before I start is I need to actually find the magnitude of the original vector. So that's where I'm going to go ahead and remember, I use the formula a squared plus b squared. So my a here is is 5 with the I, and then my b is negative 12 with the j. So I have 25 plus 144, which is the square root of 169, which nicely comes out to be 13. So it's going to make our work a little bit easier here. Still not the nicest number, but much better than having to do roots and things. So we have 13. So the unit vector we're looking for is going to be the original vector divided by this magnitude. So it's going to be the original vector divided by 13. Now, when we think about dividing, we're going to divide each part. You want to think of it more like a scalar multiplier here of 1 over 13. My original vector was 5i minus 12j. So when I divide that by 13, I'm just going to split it and put the 13 with each part. We do want to go ahead and split it here. It's because otherwise it's not really in vector form. So we're going to split it 5 over 13i minus 12 over 13j. And we're done. So that's the unit vector that we're looking for. To check the magnitude, we use that formula, square root of a squared plus b squared. Now here, our a is not just 5, it's 5 over 13. And our b is negative 12 over 13. Well, 5 squared is 25 and 13 squared is 169. 12 squared is 144 and 13 squared is 169. 25 plus 144 is 169. And 169 divided by 169 is 1. Square root of 1 is 1. So we do get the correct magnitude here. So this is the unit vector associated with the original vector. It has magnitude 1, but it goes in the same direction as the original vector. So that's what we were looking for. Now we can also write a vector in terms of its magnitude and direction. So let v be a non-zero vector, and let theta be the direction of the angle measured from the positive x-axis to the vector. Then what happens is the vector can be expressed in terms of its magnitude and direction. So it is the magnitude times the cosine of theta, I, plus the magnitude times the sine theta of j. And just a little side note, a vector that represents the direction and speed of an object in motion is called a velocity vector. So let's give an example here. So let's say that the wind is blowing at 20 miles per hour in the direction north 30 degrees west. We want to express its velocity as a vector v in terms of I and j. So the first thing I would do here is I would draw a picture. So let's go ahead and draw that little picture here. Now, you know that it's blowing at north 30 degrees west. So remember when we're talking about a bearing, we're always looking for a north-south line. So here's my north-south line. I know I'm going in the northern part of it and I'm going west. So this side is east, this side is west. So off of that line, I have 30 degrees here. All right, so remember your bearing is always off a north-south line. So we're going in this direction. So what my angle here is going to be, think about this, we're always going based on the initial positive right side. So it's going to be this 90 degrees plus this 30. Now, because we're blowing here at 20 miles per hour, that 20 is actually going to be our magnitude here. So using our formula, we have that the velocity, vector, excuse me, V is the magnitude of V cosine theta I plus the magnitude of V sine theta J. So our magnitude is 20, and we have cosine of 120 degrees I plus 20 sine 120 degrees I. Sorry, not I, J. Sorry about that. So that I and J are outside of the theta piece, so they're the variables here. Now, cosine of 120 degrees is -1/2. And sine of 120 degrees is √3/2. So cleaning this up a little bit, I have -10 for the first piece. And then for the second piece, I can do the 20/2 is 10, √3. There's not much I can do there. So my final vector is going to be -10I plus 10 √3J. Last, I want to look at an application here. So there are lots of applications that can be represented by vectors. One such example is going to be a force vector. So a vector that represents a pull or a push of some type is called a force vector. It's just a quick little picture. Obviously, it's not very good. A person holding a box or a present. So for instance, there's a force of you holding that box up, right? You're physically holding that box up, but there's also gravitational force that's pushing down on you at the same time. So again, that's just one example of how force is coming into play in a lot of different cases. So you can see you have that force going down from gravity, and then you also have a directional force coming up of you holding the box. So let's just look at an example with two forces in it. So let's say there are two forces. We'll call them F1 and F2. One has magnitude 10 and the second one has magnitude of 30 pounds, respectively, and they're acting on an object. So here you have two forces as well, acting on an object. These two would be theoretically the same, assuming that you're lifting it just enough to hold it against gravity, pushing it down. So this one's a little bit different. You have two different forces. The first direction, or for the first force, is north 20 degrees east. And that's what you see in blue here. So we're going against the north axis, and we're going in the east direction, and it's 20 degrees off that axis. And then the second force is coming in at north 65 degrees east. So that's going to be in pink, and you have that angle at 65 degrees, again, coming off the north side of that axis here. One of them has a 10-pound force and the other is a 30-pound force. So I did draw them different lengths to show the different magnitudes there. What we want to do is we want to find the magnitude and direction of the resultant force. So what does that mean, resultant? When you hear that word in reference to vectors, it always means to add the vectors. Okay, and so that may come up here or there in sections. We may say find the resultant vector or the resultant force here. So what they really want us to do is to take those two forces and add them together. Now I'm going to use the formula that we were just using that relates the force with magnitude and angle instead here, because that's the information that I have. So that's what I'm going to do to write those vectors first. So for the first vector representing the first force, again, you have that 20-degree angle, but it was off of the north axis. So we actually need the angle that's off of the positive x-axis. So that would be 70 degrees, since 70 plus 20 would give the full 90. So for our first one, our force there was 10 pounds. So it's going to be 10 times the cosine of 70 degrees times I, plus 10 times the sine of 70 degrees, and then multiply by j. Here it does ask us to round to the nearest tenth of a degree, so these are not common angles that we know, so you can use your calculator here. And when you do that, remember you're doing cosine of 70 degrees times 10, and you get about 3.42. And then here, sine of 70 degrees times 10 multiplied by 10 is about 9.40. So that would be my first vector. For my second vector, here I'm looking at that angle of 65. So the one opposite that I'm using is going to be this one here, and I'm trying to fit it in there. That would be 25 degrees because 65 plus 25 would be 90. Here, the pink one has a force of 30. So it's going to be 30 cosine of 25 degrees times I, and then 30 sine of 25 degrees, j. Now remember, I and j are vectors. Now here again, we can use our calculator. So just make sure you're in degree mode here. You're going to do cosine of 25 degrees times 30, and you get about 27.19. And then for the second one, when you multiply that, you get about 12.68 j. So that would be my second vector. Now, what we're really looking for is what's happening with the resultant force, meaning we're going to add those two vectors together. So for my I, I'm adding 3.42 and the 27.19. And then for the j, we're adding the 9.40 and the 12.68. And we get, again, this is approximate, so because all these are rounded, about 30.61 I, and then we have 22.08 j. And you would just be using your calculator there to help out. Forgetting all my little symbols. Now that is the vector, right? That's the resultant vector here, but we actually want to find the magnitude and direction. So there's a little bit more we have to do here because they don't just want the vector, they actually want those two parts answered. So for the magnitude, we'll just call this F, make it easy. Remember, it's just a squared plus b squared, and then taking that square root. So it's about 30.61 squared plus 22.08 squared. And we're just using our calculator here, so you can go ahead and do that, and you get about 37.74. Scroll that up a little bit. So I was just using the A and the B. Actually, why don't I rewrite that so it's easier to see? All right, so that was the magnitude that we were looking for. And we also want to find the direction as well, which means we need to find the angle here. So what I'm going to do is actually draw a picture first. So remember that this vector here is based off the origin. So we're starting at the origin in this form, and we're going up to the point 30.61, 22.08. So this is not to scale, but it just helps to kind of get a visual of what we have. We'll just say that's right there. We have here. So I'm looking for this angle in order to find the direction. That's the other thing we need here is the direction. So what is that angle? Think about a triangle here, right? This really looks like a triangle. We know the height here is 22.08, obviously rounded. And then we also know the length here is 30.61. Now, what happens in the picture here is this other side is actually the magnitude of that vector, right? So that length of that side is the magnitude of the vector. So we actually know that side here, it's about 37.74. So we can use trig, and there's different trig functions that you can use. Here I'm going to use cosine. So I can use cosine theta is equal to the adjacent over the hypotenuse. So here our adjacent is 30.61, our hypotenuse is 37.74, and then I can go ahead and use that inverse, right? So my theta is going to be inverse of this. Which ends up being about 35.8 degrees. And for this, you would just go ahead and use a calculator, right? We do have that inverse function on our calculator, so you're just going to go ahead and plug that in, and we do get our answer for cosine. So the direction angle for the resultant force is approximately 35.8 degrees. And over here, for our magnitude, just to make a note here that this was in. So this is our magnitude, and there is our direction.